Which one is it?
Because I think
All right.
part one.
Let's get your notes out. We're gonna jot down this little tidbit right here. I was writing this up today during first block during my Algebra 1B class. It kind of freaked them out a little bit.
Like this is tomorrow's.
Well, they're not about this tomorrow. One of them kind of looked at me, they were working, and one of them kind of looked up and said, "Wow, I'm glad I'm not in that class." Another kid said, "There's not even a single number in there, that whole thing." There is a one, yeah. So, this FTC stands for Fundamental Theorem of Calculus. Okay? Fundamental Theorem of
We've only
Calculus.
been in calculus like 6 months. We're
And
getting
now-
the first
now
theorem.
We're finally getting the fundamental theorem of calculus. Now, it really says what we've been saying for the last couple days. I mean, really, everything we've been talking about, the main concept behind all of it is that the area function is what? The antiderivative. I mean, that's it. I mean, that's the big deal. The area, what we've worked at Friday and then more yesterday, is just this realization that the area function is the antiderivative. It seems almost like we're overplaying it a little bit. I mean, we just keep coming back to it. But it is a big deal. It is that connection to the slope, which we call derivative, and then to the area, how those two connect. And that's what kind of makes calculus what it is. And so that brings in all the chart stuff then. All the stuff about f and f prime, all those connections, because f prime is a derivative of f, but f is the antiderivative of f prime. So being an antiderivative brings in all that stuff about chart relationships between two functions. So the area function has that chart relationship to little f. Okay, and so we'll continue to talk about that, and I'll continue to say these things again. There are some places in here notation-wise that can get kind of confusing. But we don't ever want to lose sight of the big picture here, the big concept, which is that the area function is the antiderivative. So it allows us to do a whole bunch of these problems that look pretty familiar to the way we did it back in chapter 1, and they are. And they should be. But what we've been trying to do is get you to explain them using area, though, right? Use area to help explain them. And then be able to do both. Be able to explain them as slope, be able to explain them as area. And understand them both ways. Okay? Let's unpack this notation here just a little bit. This first line here, if a of x is this area function, right? A is the area under little f. Then what we're saying right here then in the next line is the derivative of the area function is little f. Notice it's got x's in it though, right? Because what was the t, why was t here? Yeah, we're already using x. In this statement, we're already using x for the a, the area input. We're already using this x right here, okay? So we have to use something else, but the main thing is it's little f. But then if we do the derivative of the area function, of course the area function is in terms of x, we do the derivative with respect to x and we get little f, and it would be in terms of x. So, I mean, that's how you say something is the antiderivative of something. The way you say something's the antiderivative of something is you say if you do the derivative of it, then it gives you what you had started with, okay? I mean, so that's what this line says right here. It says, in math symbols, it says that the area function is the antiderivative. Now, the way it's usually written, though, is this right here. This is the way that Fundamental Theorem Part 1 is usually written. And the way you want to piece that together is you look inside the square brackets and it says, okay, that's the area function, which we know is the antiderivative of little f. Then when you do the derivative of that, that gives you little f back. And that's what tells you that must be the antiderivative. This is this area function thing. If we do its derivative, it gives us back what we started with. So that thing in the brackets must be the antiderivative. So that's what it's saying. But you know mathematicians, they got to make it, you know, use all this notation. Now, it says part 1. your book's authors consider this the more important part of the fundamental theorem. It's the concept part. It's the big idea part, okay? Some books would call this part 2 of the fundamental theorem because it's not all that useful to do problems with. Part 2 of the fundamental theorem, which we're going to learn at the end of the period today, part 2 of the fundamental theorem is much more useful, but it isn't. It's a result of part 1, and so that's why in this book they call this part 1. The only type of problem you'll probably end up getting in the on the quiz next week that would involve this fundamental theorem would be something like this. It might give you a problem that says, it looks like this. Oops, just made a big mistake right there, didn't I? You get something that looks like and you're supposed to write, what does that equal? And what would you write? Sine of e to the 4x. That's all you would write. Yeah, that's it. It would be one of those like on those multiple choice, and these are in the packets a lot in the multiple choice section, just like those limit problems where you're supposed to just recognize that it's the definition of the derivative. Same thing here. You're just supposed to recognize that, hey, inside the brackets here we got this, I mean, just think of this function as little f. It's in terms of t, okay, because we're using x for something else. But this is like a little f. The area function makes it the antiderivative, and then we do the derivative of it. Well, the derivative and the antiderivative cancel each other out. You just get this. But you have to put it in terms of x. If you would have written this e to the 4t right here, you're going to get it wrong on the quiz. The key is it's this inside the bracket is a function of x because of that x right there. This derivative is with respect to x. So the antiderivative would be in terms of x. The derivative would then be in terms of x. You get this. Notice the plus c doesn't matter. Notice this 3 here did not matter, right? Because the left endpoint only determines the c value. Well, when you do the derivative, what happens to the c? Derivative of a constant is 0. It goes away, right? So this 3, if this had been a 3 or a 5 or 7 or whatever, it doesn't matter. You would still get this because that left endpoint only determines a plus c, and when you do the derivative, the plus c goes away. Okay, so that you might see, but otherwise, fundamental theorem part 1 is just about the idea that the area function is the antiderivative. Okay, let's move on to the homework here. I want to talk about number 2. I guess I don't have that one here. I had mentioned this. I had mentioned last time about using the shortcut. Okay, so this is something I want you to be able to do. When you see this, okay, they told you that, and they told you little f of x was, what was it, just plain old x? Is that what they said on this?
Yeah.
Okay, and you were supposed to write a formula for a of x. Now, I would hope a couple of things will happen to you as we get more used to seeing this. When you see this area function notation with this x up here like this, that you right away think, first of all, what? When you see this area function, you right away think, well, okay, well, okay, maybe not right away. When you see this area function thing, you think antiderivative, antiderivative, okay? When you see an area function like this, you think antiderivative, okay? And so antiderivative of little f would be what? What's the antiderivative of little f here? 1/2 x squared plus c. Okay, the other thing that I would hope you would see when you see an area function like this is that hidden, not really hidden, but that initial condition that is right inside there. What's the initial condition that's right inside here? A of 4 equals 0. I just hope those two things come to mind right away. You see an area function, it means antiderivative of whatever little f is in here, and it also, this left endpoint, gives you that initial condition, which of course we know helps us find what c is. So in this problem, we would plug a 4 in for x, set that equal to 0, that'd give us 8 plus c equals 0, so c equals negative 8. So our area function is 1/2 x squared minus 8. So that's how I want you to be able to look at number 2. Okay? All right. Now let's look at 9 through 14. Okay. All right. So on 9 through 14, they give us this information right up here. Okay, now a few people, I think, when we had some work time yesterday, I must have helped with this, but not everybody, because some of you had some issues with this. They tell you a bunch of different things. They tell you what big F is, what big G is. They have different left starting points, and then here's a key element right here. What's that mean? Let's think right now in terms of area only. Why would the area always be increasing? So if, well, okay, now wait a minute. Now that, see, to me, that goes back to our slow, old way of thinking. I want to think just in terms of area for a second. And that's not bad, that's not wrong, but I want to think just in terms of area. If this is the little f graph, what's this mean for the little f graph? It's never below the x-axis and it's never below 1. So here is 1 right here. Okay, so this graph, we don't know where it is, but it's always up here somewhere, right? It could come back down, whatever, but it's going to stay above that dotted line, right? So, which a consequence of that would mean that these areas, big F and big G, are going to be what? Always positive and always increasing, because whether you start from 0 and go to the right or start at 5 and go to the right, you're going to be picking up positive area, okay? So now it says, why is big F of 7 bigger than big F of 1? Well, big F starts at 0, right? The area, again, if we're going to talk area, now let's be specific here. The area is always increasing. So big F of 7, and again, don't forget this right here. Chase, you with me now? You didn't have this part of the homework done, so I want to make sure you're understanding this, okay? And talking to Matt isn't going to help that, right? So I got big F is the area from 0 to x. So if I'm going to talk about big F of 7, then I want everybody to really be clear about this. When I see big F of 7, that means a 7 goes right there in for that x, and that also means a 7 goes right in there for that x, right? So this is the area from 0 to 7. So because that function looks like that, that area is positive. Okay, what's big F of 1? What's big F of 1 represent? The area from 0 to 1. The area from 0 to 1. So that would be this piece of area, right? Well, 7 is to the right of 1, since the area is always increasing. All those kind of things. A picture would be good too, okay? But in terms of area, it means that. Okay, now let's back up and let's talk about this in terms of slope. See, this don't make the same mistake we made back in chapter 1. I don't know how many of you people that I talked to during these quizzes we had in late chapter 1 and early chapter 2, and I just never quite understood that chart. I just never could quite get that figured out. And whatever. And I told you when we started this chapter 5, I said, don't make that same mistake. Okay? Maybe as you went through some of these questions, they seemed pretty easy on the surface. You could get kind of the answer, and you could get yes, it's increasing, or no, or whatever. Some of you had 3 pages of stuff written. That's great. Some of you had barely anything. Okay? So when I see that, I think, well, you got a little bit on the surface, but that scares me a little bit about this quiz coming up Thursday, okay? About how well we know this stuff, Okay? So what I'm trying to do here is go through this, all the different ways we can think about these, what these things are. There's plenty of places to get confused. I understand that. And I think some of you are probably thinking, well, I think you're making it more confusing by keep explaining all these different ways of looking at it. And that may feel that way, but I want you to see all the different ways of looking at it. I don't want us to just kind of know it on a surface level. Zach, what's your question?
Is t equal to x? Like, if x is 1, would t equal 1?
Okay. T, and that comes back to this right here. Okay? For this function right here, we're talking big F and big G are the areas under this little f graph. And in that little f graph, this is the t-axis. Okay? So when I draw this little f graph, this is the t-axis. So when I say t greater than or equal to 0, we mean from here on over. So we mean little f is going to be positive for here on over. But when I put a 7 right here, or a 1 right here, I'm putting them into the big F, and so that's going in for x. Those aren't t values now, those are x values.
But how do they relate to each other?
But they are the same, you're right. In other words, when we say a 7 right here, we're talking about the area from 0 to x, because that would be like this being an x, right, which is on the t-axis. So yes, x and t represent inputs. You see what I'm saying? But x is representing a specific input. T is representing all the inputs of the little f function. Okay? I don't think for anybody else here, I'm not sure that's a big deal, but they are both inputs. They are both inputs. Okay, so back to this question now. Let's talk about it not in terms of area, but let's talk about it in terms of the chart. Okay? So we see this funny looking symbol, this area function symbol, and we think right away what? Antiderivative. Now, this is something that if it was a free response question, I want you to start getting in a habit of when you see these area functions. Because this is something on the AP test they're going to want to see, you're going to need to make that connection. Them giving you this, and matter of fact, I don't want to take time right now, but if we pulled out some of those old packets and looked at some of the free response questions, the ones we didn't do, you'd see a bunch of them that have these area function problems written here. Okay, they're pretty common. As soon as you see that, that is not automatic that that's the antiderivative. You have to show them that you know that. Here's the quickest way to do it. You just write down big F prime equals F. Whenever you see one of these, and likewise big G prime equals F, get in a habit of just writing that down. Because what you've done is you've made that connection. You've now said, okay, I can do all the chart stuff with big F and little f now, and big G and little f, because I've made that connection. So now let's think of it that way. So now, okay, now we're talking about little f being the derivative. Okay? So now, Derek, go. What does this mean if little f is greater than 1?
Because little f is always positive, then big F is always increasing.
On the chart, little f always positive, slope's always positive, big F's always increasing. Keep going.
So then if you're going from 1 to 7, it has to be going up.
It has to be going up. But see how that's a different explanation than the one about area. It gets us to the same place, right? In one we say, since little f's above the x-axis, our areas will always be increasing because we're picking up positive area. The other one is to say if your slopes are always positive, then the graph is always increasing. Big F's always increasing. They both get us the same place, but they're two different rationales. And to be honest, on the quiz Thursday, I don't care which one you use. I don't care if you use area or if you use slope or the chart rationale or whatever. Okay, it kind of depends on how the question's worded, probably. You'll probably be able to tell that. Okay, is big G of 9 greater than big G of 5? Reason? Same. 11? True? True? Is big F of x greater than big F of 0? Reason? Same. Right? 9, 10, and 11 really were the same exact reasons. Big F of 0, the slope would be 0. Of course, we talked about that too. That's your initial condition you're given. Big F of 0 is 0. Okay? So that is going to be 0, and we know the rest of the areas are all going to be positive, and this goes back to what Zach was saying. See, it says x greater than 0. That's the same as the t. I mean, it really fits together with the t. But 3 different ways, though, of asking essentially the same thing. But it's the same rationale in all of them. Okay. 12, I think I had helped some of you guys with, so we'll skip over that one. 13, okay. I think I had asked you, remind me now, because we get 2 classes, and I sometimes get confused which we talked about. I think I'd asked you yesterday, what is this one dealing with, 13 and 14? Speed limit law. Okay, now remember you guys answered on that, but then I don't think I helped you much more than that. Okay? Now, speed limit law was dealing with slope. Okay? So that would be saying, okay, if the slopes are always 1, and what's the other part of the speed limit law that we don't have written down here? If this is big F, I'm going to make this a big F graph right here. What am I missing here from using the speed limit law? Slopes are always bigger than 1. And what happens to big F out here at 6? Right? That's the question. What is big F of 6? What am I missing? Starting point. What's my starting point for big F?
0.
Big F of 0 is 0, right? That thing I told you over here a minute ago that I hope you always see when you get an area function, that you notice that big F of 0 is 0. So if we're going to start big F at here, and the slope is always 1, that means if you go over 6, you've got to go up 6. So big F has to be 6 or more. Actually, it couldn't even be 6, could it? Yeah, go ahead.
That's what I,
Well, okay, yeah. Since little f is greater than 1, wouldn't it be true to say this, that big F of 6 will have to be greater than 6? Right? It'll actually have to be greater than 6. But is it wrong to say this, though? That's still true. Big F of 6 is going to be greater than or equal to 6. It won't ever be equal, but it'll be greater than, so that's okay. So it's not wrong to put the line under it, but it wouldn't be necessary. You could do that. Okay? But now let's talk about that in terms of area. Here's a part I don't know if we've talked about. Let's talk about this in terms of area. Forget slope. Forget speed limit law. Did I help anybody? I'm not sure I helped anybody in this part of it. I'm not sure anybody asked. In terms of this graph, how could we tell that big F of 6 would always be greater than or equal to 6?
Because every time you go over 1, you're getting at least 1 box of area, because it's always greater than 1.
Let's come back to here. Yes, that's very much related to that. Right here, when you see big F of 6, and this is big F of x, what's big F of 6 mean then? Big F of 6 means the area from 0 to 6. Well, look at the area from 0 to 6. Isn't the area from 0 to 6 guaranteed to have that much area? There's a strip of area that's 6 that is guaranteed to be there, and probably more. See how that's a whole different rationale, a whole different line of reasoning for the same problem? See, that's what's so cool about this stuff, that connection between slope and area. All these things that we argued before back in chapter 1, we can re-argue again with a whole different set of circumstances.
Just like arguing.
All right, what about this one? Is it possible that g of 10 is equal to 3? Well, let's first talk slope. Again, since it's g, what do we know about g? G of 5 is, we know g of 5 is 0 from right back here. G of 5 is 0. So therefore, g of 10, well, if you're at 5 right here and you're going to go over to 10, you go over 5, how much you got to go up? If the slope is 1, you go over 5, you got to go up at least 5. So there's no way g of 10 can be 3. Right? No way g of 10 can be 3. It's got to go up at least 5. Okay, let's argue it from an area standpoint. Same thing, g of 10 would be the area from 5 to 10. G of 10 is the area from 5 to 10. That's putting a 10 right in there. Well, the area from 5 to 10 has to include this strip of area. That's how much? 5. So the area from 5 to 10 has to have an area of at least 5. Okay? So it can't be 3. Again, same conclusion, just a little different rationale. Yes?
So big G of 5 is 0, but it says that the little f graph is always greater than 1. Does it just like jump?
No, because remember, big G is just the area under little f, the same little f graph as this one.
So is the little
Remember, different left, yeah, it's a vertical shift. Little f never changes here. Little f never changes, but if you were going to look at a big G graph or a big F graph, the difference between big F and big G would be that vertical shift. See, because what I think I'm hearing what you're saying, big F of 0 we said was 0. And we're saying big G of 5 is 0. So big F and big G cross the x-axis at different places because of the vertical shift. Am I answering that?
Yeah.
Okay.
So the little f graph doesn't have to cross at 5 for the area to be 0.
Right.
That's
Just
okay,
the
yeah,
end.
yeah.
That's right. That's just the endpoint. So what? Right. So I think I see where we're going with that. How can if the little f graph is always up here above 1, how can the area at 5 be 0? Right? Well, that's because, yeah, that's right. That's because it's defined to be, so if I have x over here, so this, again, this comes back to what Zach was saying earlier. If x is on my right side of 5, what kind of area is this? Positive. But if my x is on this side of 5, if I'm going backwards, what kind of area is that? Negative. So to the left of 5, I've got negative area. To the right of 5, I've got positive area. So it makes sense right at 5, I've got 0. Okay. That's where this, right there where you just said that, is where this can get confusing. Okay? And old Daniel, he's watching the video here, and he didn't see what, that's okay. It's just Daniel. So it's funny how you can, with this notation stuff, how you can kind of, I mean, it makes you stop and think, much like it did back when we were doing a slope. And every once in a while you had to stop and think, wait a minute, slope increasing, that's this, whatever. And pretty soon you just kind of went off the chart. Well, the same thing's going to be true here. The chart is going to work. I mean, it's just going to, because we've got the antiderivative. The area function is the antiderivative. So all this stuff about local max, local min. You'll see, I'm going to give you some problems today, and you'll get all confused again, probably. And so that's fine. I mean, we'll work through it. But and I want you to. I want you to think your way through those things. Okay. All right. The other. Okay, the other thing I want to look at is on page 320. So that's all I wanted to go through on the homework there. I wanted to go through one where we draw a graph with an absolute value. We talk about an antiderivative with an absolute value. And see how that might change things here. So this will be part of your homework. So we're going to do this together. This is 39 through 44. Okay. Okay, this is how your book defines it. So you can bet on the quiz we're going to have a number of problems that are going to deal with this area function, okay, and ask you different questions about it, come at it from different angles to just really see, how well you can handle the notation and understand the concept. Now, I also want to write it with little f written in there because sometimes we write it with just little f of t dt and we define little f separately like this one does. But a lot of times we don't do that. Instead of taking 2 lines to define this, a lot of times they'll just put little f right inside the integral. Well, what would little f be if I wrote it inside the integral? 2 minus absolute value of t dt, okay? So this is how I would define that using just 1 line as opposed to 2 separate lines like they did. Okay, so in 39 they want us to write a formula and then graph it. And again, I want to do this one more time, even though we've already seen several examples of this, and we've already looked at, let me give you another one. We've looked at pictures like this, and I've got another one here, right, where we could take this, oops, that's not what I wanted to do. Just grab this part. There we go. Okay, so we've already looked at several examples where the blue graph is little f, and the yellow, the gold, is the area. So right here, I'm sliding along, picking up positive area, so my area graph's going up. Okay, right here, I quit picking up positive area, picking up some negative. So the graph's going down. Right now I have no area because they're canceling each other out. Now I'm picking up, I have negative area now, but so my area graph's still going down. Right here I start picking up some positive area, so it comes back up. And it kind of flattens, but I'm still picking up area. So the area graph keeps going up. So again, all those things about the chart and that kind of stuff. So we've already seen it, but we want to do one more here where we kind of do some of it by hand. Graphs of my hand, see these same connections. All right, so what you're supposed to do is, in 39, is find a formula for a of x. Now, unfortunately, we don't have an antiderivative for absolute value. So we actually have to treat it as a piecewise graph. All right, so let's take and graph this little f. Okay, what would that graph of little f look like? This is all going to be no calculator on Thursday. So you need to be able to do some of these basic graphs. Upside down V, up 2. And since it's a slope of 1, that's going to cross here at 2, cross here at -2, cross up here at 2, like so. Okay? So what is the equation of this piece of the V, the right-hand piece? What would be that equation? -x plus 2, right? Have a slope of -1. Okay, and what about this piece over here? That would be just x plus 2, right? That would have a slope of +1. Okay, and then what's the other thing we know about big A? What's the initial condition we know? A of 0 is 0. We know that, right? If we put a 0 in for x right there, the integral from 0 to 0 is 0. Okay, so now we can do kind of that shortcut we learned yesterday. We can do our antiderivative. So we're going to have 2 pieces to this. We're going to have the left-hand piece and the right-hand piece. Let's do the left-hand piece first. What's the antiderivative of little f? 1/2 x squared plus c. Now, on the quiz Thursday, there'll just be some basic antiderivatives, not killer antiderivatives. That's what we'll be looking at next week, but some basic ones, and you will get to practice some more tomorrow. We'll be spending some time practicing some of just the basic ones. Okay, and what about the right-hand piece? All right, and then what's the c value? Well, we put in our initial condition, put in a 0. Oh, that's pretty easy. Yeah, c is just going to be 0. So the c is just going to kind of disappear. All right, so they wanted us to graph. Both little f and big A on the same axis. So in blue here, let's go ahead and graph these parabolas. Now, we should be able to do this without a calculator because we know it's an antiderivative. First of all, let's do the one on the right first. Let's see which one's the one on the right. That's this -1. Okay, let's do this one. So let's plot a couple points in there. Easy one is 0, 0. We know that point. Okay, we already knew that one. Okay, it's going to be an upside down parabola. The question then becomes, do we know where its peak is going to be? do we know, like for example, if I plug a 1 in, okay, let's just plug a 1 in. So we plug a 1 in here, we get negative 1/2 plus 2, so that'd be 1.5. So at 1, I'm going to get 1.5. Okay, so up here somewhere. Okay? And then if I plug a 2 in, I'm going to get 4 times that, that's negative 2. Negative 2 plus 4 is what, 2? So at 2, I know I'm going to get 2. Now, and now I could keep going. I could plug in 3. I get 9 times that, that's negative 4.5 plus 6. Negative 4.5 plus 6 is what? 1.5. Now, wasn't that the same point I had there? So because of symmetry, doesn't that mean that has to be the max? Is there a reason I should have known that's the max? Positive to negative, right? I mean, all that chart relationship is there, right? I'm graphing the antiderivative right now, so the black thing should be the derivative. It goes from positive to negative. It's 0 there. There should be a slope of 0. It should be a local max, okay? So again, all those things fit. So that's that piece. It's an upside down parabola, and the peak is there. And so what's going to happen on this other side? We're going to have a parabola that opens up, and what's its peak going to be? Right there, it's going to be a local min, because this goes from negative to positive, right? So if I put a negative 2 into, which one are we doing, this one? Negative 2 in there, so that'd be 4, that'd be 2, plus negative 4, that'd be negative 2, so that'd be right down here. So it's just going to come down and be that sort of a thing, almost like a cubic. It's really two parabolas kind of hooked together, but it's really like a cubic. Or it looks, kind of has that look. And sure enough, and the whole point of this section, and if you go, we'll just quickly run through 40 and 44 here, and you can jot something down because this is going to be part of your homework. But again, the whole point of this was kind of like, the authors of the book, when they wrote this exercise, they didn't know we had this sketch pad, the computer models we've looked. Ooh, didn't show up very good. This is just one last time. This might be the last time we throw this up here, but one last time of seeing an area function and then actually kind of graphing that area function and saying, yeah, hey, look, it's the antiderivative. It's the chart. The chart stuff's all over that. Because if we go to 40, where's the area function increasing? Well, the area function's increasing here from negative 2 to 2. What's little f during that time? Positive. Okay, the area function's increasing when little f is positive. That's what the chart had said before. Where's the area function decreasing? From negative infinity to negative 2. What's little f then? Oh, it's negative. Same thing from 2 to infinity. Area function decreasing, little f negative. Okay? 42. Where's the area concave up? Now it's concave up from negative infinity to 0. What's little f then? Increasing. Yeah, that's right. When little f was increasing, the antiderivative, big F, big A, is concave up. And likewise for 43, concave down when little f is decreasing. And then 44, where does big A have an inflection point? Right there at 0. What happens on little f? It has a local max. Remember, we changed from increasing to decreasing. Big A changed concavity. We talked about that. Local max and mins of little f has inflection points of big F. So again, just one last time to reinforce this idea that the area function is the antiderivative. And all those connections that we've learned before come along with it. Yes, there are some technicalities in the notation, and this whole idea of left endpoint and moving right endpoint. You change the left endpoint, changes the plus C and all those, and you're going to get to deal with those in just a minute or two here. All right. So I'm going to give you some time to work on that, and I think what will happen are some questions are going to come up. I want you to work together, to work through and try to explain to each other, and at some point I'll probably step in and help clarify a few of those things, okay? So there's going to be two parts to the homework here. So first, here in this same section, we're gonna do, you're gonna work on 51 through 56. Okay, that's one section that's got its own set of issues and things that are gonna come up. Matter of fact, we'll probably spend a lot of the next half hour or more working on those and thinking our way through those. Okay, and then you're gonna do 61 through 64. Okay, and that is going to lead us, as you work through those, the last 15 to 20 minutes of class, you'll be working through those, and then we'll be talking about them. That's going to lead us into the fundamental theorem part 2. Okay, what that is. And then I'm going to assign you, then we should be pretty much done with those. Then I'm going to assign you some more out of section 5.3. And 5.3 is really just now applying those things we've learned. So it's mostly more questions about the chart and those kind of connections. Okay? All right, so take about the next, well, probably the next 20 minutes or so to work through 51 through 56. And talk it over amongst yourselves and make sure you're, and as you got questions, come and ask me, that's fine. At some point, probably in the next 15 or 20 minutes, I'll step in and help talk about some things. No. Yeah, go ahead. Yes, sir.
On 39,
Uh-huh.
we got that wrong.
What's that?
Well, it says from 0 to X, so we do not graph the negative. Or like,
Say, okay, come up.
it says from 0 to X.
Right.
Not graph.
You can go back. Right. You can put a negative 2 in there. You'd have the area from -0 to -2. So the area from 0 to -2, since you're going backwards, this would be negative area.
Alright.
Yes.
Above the x-axis, increase and equal 0 at 3.
So from 7.1 is here for each, is great. What?
And then
So it should still be the same.
Then add -1. It's still decreasing, but I decreasing, right? So it's so it's talking about and then add 1. So it's just from negative to positive again. And then 3.
Now, I've answered, now I know kind of what classes in the past have done, I know what second block did, and the first two people have asked me questions already on local max and min on 53 and 54, right? How many people, when you're asking that question, are looking at the 2 and the -3, that left endpoint, as a factor in there? Is it a factor? And are you considering it to be a factor? Yeah, you are, aren't you? I mean, you're kind of, don't you want to? I mean, you're kind of going, oh yeah, well, then, okay, but this one starts at 2, so then it would be just, and that's great, that's great. I'm glad you're thinking about that. Matter of fact, Chris, what Chris just asked me up here was on this one about the area, this area going from 0 to X. So if we go from 0 to X, how can we have area back here? Well, yeah, remember, because we can go backwards, right? So if you want to go this way on our area, remember, here's our black graph, we're doing the area under the black graph. So as I go back this direction, that's backwards because I'm starting at 0. As I go backwards, what's this area here? Negative. So what should the area graph do? Should go down, right? And sure enough, it goes down. Okay? Now, we talk about going backwards on this one. Isn't this still a local minimum right here? Right? A local minimum is when little f goes from negative to positive. The fact that we started at 0 doesn't matter, right? The only thing that mattered is, since I started at 0 on this one, as I went this direction, I was having negative areas, so the area was going down, and then what's this area under here? What's this area here under the black? Since it's below, but I'm going backwards, that's positive, so my area starts coming back up, so I get a local minimum this way, as opposed to our normal way of getting a minimum, which is left to right, right? This way. What if my left endpoint would have been over here at -7? What if this would have been a -7 right here? Then we'd have come this way to get our area, right? So as we'd have come this way to get our area, what would this area be? Negative, so our area graph would have went down. Until right here we start picking up positive and it goes up. It's still a local minimum, right?
So no matter where it starts, they're all gonna have the same,
it's going to be the same
like
graph.
max and min.
Okay, so yes. Because what does the different left endpoint mean? I mean, let's just get into it now. It's the plus C, right? The different left endpoint, this 2 and this 3 are just the plus C, the shifts. Well, if you take a graph and just shift it up and down, does that change where the local max is? Does it change where the local min is? Now, it changes the output of the max and the min. So that's something we'd have to consider. But it doesn't change where it is. Does it change where it's increasing, decreasing, where it's concave up? Any of that chart stuff doesn't change. So how you handle it is totally up to you. Some of you will look at it and say, you know, if they ask me about G and H here, I'm just going to, I don't care which one, 2, -3, doesn't matter. I'm just going to start over here at the left and just go this way like I always used to with the chart stuff. And that would be just fine. Now, others of you may want to actually sketch a big G and a big H graph, a real rough one, but sketch it, because we did that back in chapter 1 as well. And if you want to do that, I think that could help you get over this kind of not, you know, this thing of, well, that left endpoint should matter. So if you want to, otherwise just keep working, but I'll just talk through what a graph of this, a graph of G and a graph of H would look like. Let's do graph of G first. Now, what's the initial condition I know with G? At -3 at 0. So over here at -3, I know I'm going to have an area of 0. Okay? Then, from here, what happens? Well, this area is what? Negative, getting more negative. Then it's negative and getting, or littler chunks of negative, right? So my area graph's got to go down. It's going to be going down and going down steeper. And then it starts coming down less steep. And then what happens right here to my area at 1? I start picking up positive area. So this has to bottom out right here, right? Now I'm going to start picking up positive area the up, and then it's going to kind of let whatever, but I'm picking up some positive area till there. Okay, but now let's go backwards. Let's come back here. What kind of area do I get when I go to the left here? What kind of area is this? No. As I go backwards. Negative. So what's this area graph right here at -3 have to do? It's got to come back down. So there would be my G graph. So now let's go ahead and plot the H graph. Okay? Now what's different? Well, the H graph starts at 2. Okay, fine. At 2, we're going to have a slope of, or area of 0. Good enough. And then here's 2 right here. And so now I start picking up what kind of area? Positive and getting more positive. But then I pick up more positive. It's kind of leveling off. Okay, fine. So it looks like that. Now what happens when I go to the left of 2? Well, what's this little piece of area? This little piece of area here is negative because I'm going backwards. So that means this graph has to kind of go down for a little bit until 1. Then what do I pick up? What's this area? Since I'm going backwards, this area is positive. So I'm picking up positive area, getting more positive. And then I'm picking up littler chunks of positive until about here. Until where? Well, that's what? -3. And then what am I picking up here? I'm going backwards, remember? Now I'm picking up some negative, so now it's got to go down. Well, look at that. Look at the big G, look at the big H graph. They're the same graph, aren't they? They're just shifted up and down. So the fact that I had started 1 at -3, 1 at 2, all that really is what Derek was saying earlier. It's where it crossed the x-axis, where it had 0 area. But my local max is still at -3 in both of them. My local min is still at 1, right? So I guess a lesson from that is that when you see these two different things, you just say, hey, G and H are both antiderivatives. They have different left endpoints, which means they'll have different areas, okay, at certain points. But as far as where the area graph's going up and where it's going down and where its local max is, where its local min is, that's all based on this same little F graph. So those things don't change. This goes from positive to negative, that's a local max. This goes negative to positive, that's a local min. Here's a local max on little f, that'd be an inflection point. -1 would be an inflection point. On both graphs. Both graphs. Now when you get down to 55 and 56, now you want to find their actual max and min values. Yeah, now you have to actually find some areas now. Right? On 55 and 56, when it talks about max and min values, wouldn't list of candidates be appropriate? Wouldn't list of candidates be appropriate there? That's an absolute max question. This is little f. Where are your candidates? Where do you look for max and mins? At your endpoints? Let's do 55 is G. Your endpoints. So you'd be wanting to check G of -5. You'd be wanting to check G of -2. Those are the two endpoints. Where else? What's the derivative of G? Little f. Where? So you want to see where the derivative is 0. The derivative is 0 at -3. Right? Now that one only goes -5, -2, so wouldn't that be a list of candidates, right? Now, how do you find G of -5? How do you find G of -5? Yeah, you come back to here. What is G? G of -5 is the area from -3 to -5. That's going backwards, so that'll be a negative area. It's the area of that triangle. Okay, so see, you should be able to find all these areas. Okay, I'll let you go. I said too much. Okay, so go ahead and, but it's an absolute max and min problem, so it's really a list of candidates. And there are areas you can actually find because they're part circles and triangles and whatnot. Well, so what do you do when you say G of x? Were you just going from -3 this way? But G of x would also have values going this way too. But you found to go from -3 to 5, you really found G of 5. I think that's right. Yeah, see, then that's not really what G is. Really, you didn't know how many values G is, right? That's what we just found. G of each one. So therefore, the values of them are only going to be different by some constant. They're only going to be different by that piece of area from -3 to 2. Yeah. Give a graphical explanation. That's all. That's all. You can. But you, since you're doing a list of candidates, what you need to do is be able to compare it. It's going to be from -3 to -2. You're going left to right. So it's going to be a negative piece of area. It looks like it's going to max it. It's clear, but yeah, there wouldn't be a way to find that exactly. Not using geometry anyway.
Oh, we can find the values. Good job, John.
You guys get done with those other ones? Did you get done with 61 through 64?
No.
Okay.
Are those the ones where you go, like, do the derivatives?
No. Actually, don't have to do it.
Oh, geez.
As you get to 61, as you get to,
Still recording. Okay.
61 through 64, there's two things. What they want you to do is write it in terms of big F. Okay, so all you're going to have is like big F of something, right? I mean, big F, you're going to have just in terms of big F. But something you may need to use are two of the properties that we talked about the other day, which is, this is a, I don't know if this is exactly how we wrote it the other day, but this is one version of that, where the integral from A to C plus the integral from C to B would equal the integral from A to B. Okay, that's one. And then another thing you might use is this idea that the integral from A to B,
Better freeze this.
okay. Oh wait.
For that crazy stuff going on over there.
All right. So, all right, that was one property, and then we had another property that said the integral from A to B of little f is equal to the opposite of the integral from B to A. Well, if you switch them around, then it's opposite. Okay, so I'll let you think on that just a few more minutes, and then we can talk about those. All right, how many people have something down for like 61 through 64? Some stuff. Okay. All right. Well, that's probably enough here to look at this so I can give you a chance to get going on the other thing. This is the part, 61 through 64, this is the part that's going to lead us into this idea of the fundamental theorem part 2. Okay? That you're given big F is defined to be this. Now notice, I think I warned you about this the other day, that they kind of switched it on you. They put T in here this time. But that's okay, it doesn't matter. But T is the important variable in this definition. T is that, and T matches up right there. That's the right endpoint. So then here we have to have something other than T. Right? So they put X, whatever. Also, notice in these down here, we used U and Z and T and U. It didn't matter because these are all definite integrals. Now, we've spent a couple days really focusing on these area functions, these functions that go from 1 to X and 1 to T or whatever. But then we got to remember that where we started with this was just the definite integral, which was a fixed piece of area, which is just a number answer. Right? And we're hoping to find a way to find those areas. Yeah, we can find trapezoids and rectangles, but what about under a parabola? How do we find that area? Okay? What's going to be the shortcut way to find that area? Well, that's what this is going to give us. So in 61 through 64, we have these definite integrals, but we have big F defined as this area function. Well, hopefully you found 61 kind of easy. 61 is just what? Big F of 4. Okay, I mean this is the integral from -1 to 4, and big F is defined to be the integral from -1 to t. So if you put a 4 right here, that means put a 4 right there. So that's just big F of 4. That's all they wanted on 61. Okay, now, and then 62, they say, okay, what about this one? Well, what's wrong with that? -1's in the wrong place. So how about if we switch it around? Make it opposite. Wouldn't that be true? Okay, whatever, we get that there. Well, what's this equal to then, in terms of big F? Negative big F of 0. Everybody okay with that? Okay, this is just kind of rearranging the notation. All right, then you get to 63, and the issue there is there's no -1 anywhere. Well, that's where that top property on the board over there comes into play. And that is, that property says that this integral from -2 to 3 is the same as the integral from -2 to -1, okay, plus the integral from -1 to 3. It doesn't really matter what we have in this location where the C's are. It doesn't really matter what's there. As a matter of fact, it doesn't even have to be in between -2 and 3. That doesn't matter. So now we get this. Well, now that, okay, we look at this. We say, well, look at that. That's big F of 3 right there, right? And this is what? Big F of, we have to flip those, right? We have to flip those, so it'd be negative big F of -2, right? And so we would get that. So far we've got this right here and this right here. And then we could do the same thing on this one. We could make this go from 0 to -1 plus -1 to 1. It doesn't even matter that the -1 is not in between there. Okay, that doesn't matter. Well, so what do we get? This here would be big F of 1. And this would be, flip those around, this would be big F of 0. Now, as it turns out, this is not something you're going to have to do on a routine basis to be able to solve these definite integrals. What we are going to notice here from what we just did is we're going to notice a pattern. Okay? We're going to notice a pattern. I'm going to work my way backwards here and put it in blue. On 64, I'm going to flip those around. I don't like that negative in front. I'm going to flip that around so it's this. Okay? Everybody okay with that? Now remember, what is by definition, what is big F up here? Big F is what? Area, but the antiderivative. Big F is the antiderivative of this guy in here, this little f, right? Big F is the antiderivative of this. What we have just said is to find this area. We can take the antiderivative of this guy right here, plug in a 1, take the antiderivative of this guy and plug in a 0 and subtract those, and that will give us the area. That's a pretty big deal right there. That just gave us a way of finding this definite integral if we can find the antiderivative of this guy right here. Now it turns out this doesn't have an antiderivative. As we'll find out next week, not all functions have antiderivatives, so we'll have to have a backup plan in those cases. But if it has an antiderivative, this is going to be very powerful. X squared, for example, has an antiderivative. So we'll be able to find the area under a parabola by doing this little technique. Look at this right here. Let me just rearrange this one. This would be f of 3 minus f of negative 2. Right? Hopefully you're noticing the pattern. F of 3 minus f of negative 2. Well, now what should this one have been? What should 62 have been? It should have been f of negative 1 minus f of 0. But go back to here, we already know that big F of negative 1 is 0, right? We know big F of negative 1 is 0. So if you look at this, sure enough, that is the same thing. And this one should have been big F of 4 minus big F of negative 1. And again, big F of negative 1 is 0. So that was true as well. That is really a pretty powerful idea right there. Matter of fact, it is the fundamental theorem part 2. So now I told you earlier that the fundamental theorem part 1 was the main conceptual idea. It's the one that tells us the area function is the antiderivative of little f. It's the thing that connects derivative and area, slope and area. Okay, that's a big deal. Allows all this to happen. But it's not that useful in problems. Well, the fundamental theorem part 2 is really useful because what it says is anytime you want to do a definite integral, right? This is from a to b now. Anytime you want to do a definite integral, you simply take the antiderivative of whatever you're doing the area of, plug in the right endpoint b, plug in the left endpoint a, and subtract them. And that will give you the area. That's very useful. It's a result of what we learned about fundamental theorem part 1. But this is what we just learned in problems 61 through 64. Okay, so the second part of your homework today. Now, I'm not going to give you any that use this fundamental theorem part 2. That's what we'll pick up tomorrow. Okay, we'll pick up tomorrow with this fundamental theorem part 4. We'll work through a few examples, and I'll give you.
What happened to part 3?
We'll pick up with this fundamental theorem part 2, and I will give you some examples, and then we'll work through those. But the rest of your homework for tomorrow is just going to be, it's in section 5.3, but really section 5.3 is just kind of a culmination of what we've been doing. So there's still more chart kind of questions, those kind of things. So you're going to do, I think it's 1 through 8. Let me look here. Yeah, it's 1 through 8. And that's one section with a graph, and then you do your chart kind of questions. 35 through 38 is another one of those kind of things. And then 43 and 48. Okay? So that's the rest of what we have for tomorrow. Then we'll pick up and we'll talk about those. We'll finish the rest of section 5.3. We'll do those LH ones that we have left there, and then the quiz will be on Thursday.
gondolas. So is it just like